So let's take a look at some examples of some Lewis structures. So we'll start off with BF3. So at this point, you want to go ahead, pause the video, work through this, and then we'll reconvene and do it together. All right, so hopefully you pause the video and solve this. So when you think about Lewis structure, first step is counting valence electrons. Boron has 3, fluorine has 7. There's only one boron, so that's just 3 valence electrons from there. There's fluorine has 7 valence electrons, and then there's 3 of them. That's 21 valence electrons for a total of 24. We put the least electronegative atom in the center, which is going to be boron. Fluorine is the most electronegative. And then we'll put the fluorine simply around it. We'll draw 1 bond to each. That's going to use up 6 valence electrons, so we're left with 18. And now we're going to give octets, starting with the most electronegative element. So that's the fluorines in this case. And so when we put 6 around 3 of them, that is 18 electrons. So that gets us down to 0 valence electrons left. So now you might be thinking to form double bonds, to form to give boron an octet. But remember, boron is an exception. It does not want an octet. And you can kind of double check this by thinking about the formal charges, right? So let's think about the formal charges of boron. Boron normally has 3 valence electrons. Here it's got 3 bonds, no lone pairs, so a 0 formal charge. Let's think about the fluorines. They're all the same, so we'll just do 1. Normally has 7 valence electrons. Here it has 1 bond, and then 6 lone pair electrons, not lone pairs, but lone pair electrons. So 7 minus 1 minus 6 is 0 as well. So you can see we have all 0 formal charges. So if we try to do any kind of double bond stuff, it's going to mess up the formal charges. So that is the correct Lewis structure for BF3. Next up, we got Nh3 Ammonia. So again, go ahead, pause the video, work through this, and then we'll do it together. All right, so hopefully you pause the video. Let's take a look at the valence electrons for Nh3 first, right? If we take a look at our periodic table, nitrogen has 5, hydrogen has 1. So 5 times 1 is 5. 1 times 3 is 3 for a total of 8 valence electrons. Hydrogen is always terminal, so nitrogen then goes in the center, and then we'll put the hydrogens kind of nicely around it. Single bond to everything first. That brings us down to 2 valence electrons. Nitrogen is missing an octet, so we give that the 2 electrons. And so this is what we're left with. If we think about the octet rule, nitrogen has an octet, hydrogen has a duet, so everything is happy. And then if you go ahead and calculate the formal charges, you'll see that our formal charges are all 0 as well. Next up, we have Nh3, nitric acid. So go ahead, pause the video, work through this, and then we'll reconvene. All right, so hydrogen, nitrogen, and oxygen. Hydrogen has 1 valence electron. There's only 1 of them, so there's 1 electron. Nitrogen has 5. There's 1 of them, so that's 5. Oxygen has 6. There's 3 of them, so that's 18. If we go ahead and sum this up, we'll get 24 valence electrons. Hydrogen is always terminal, so, and then oxygen is more electronegative than nitrogen, so nitrogen is the least electronegative, so it goes in the center. And then you have to kind of be careful, right? H and O, remember one of our tips is that OH is a common motif. And so this is something that you see here. And anything that kind of generally, any oxy acid, which nitric acid is, will generally have this motif. So how do you know this right off the bat? This is just kind of where practice comes in handy. So what ends up happening is we surround this nitrogen with the oxygens, and then we put the hydrogen next to the oxygen. 1 bond everywhere. That's 1, 2, 3, 4 bonds, 8 electrons. That leaves us with 16 valence electrons. Next, we'll put lone pairs, starting with the more electronegative atom. So we'll put 2 here to give that an octet, 6 here to give that an octet, that's 10, and then another 6 here to give that an octet. So that goes down to 0 valence electrons. Nitrogen here does not have an octet, so we want to give it an octet. So next thing we have to think about, where are the electrons going to come from? Which oxygen are they going to come from? And so one hint you can use is formal charge. So go ahead, pause the video and find the formal charge of everything. All right, so hopefully you pause the video. Let's take a look at the formal charge. Oxygen or hydrogen here is 0. This oxygen is 0. This nitrogen is +2, right? Normally has 5 valence electrons, only 3 bonds here. 5 minus 3 is 2. This oxygen is a -1, and this oxygen is a -1. So when we have this plus-minus scenario, we can create bonds, right? That's where you want to create bonds from. So we won't do it from this oxygen because that's already at 0. So moving its electrons is going to mess up that 0 formal charge. So we've got to pick one of these two. So let's go ahead, just pick one. Move these down here. And when we do that, you'll see that this formal charge goes to 0 and that this formal charge goes to +1. And so now everything has an octet. The next thing you're thinking about is, hey, I want to reduce my formal charges. And so one thing you might be thinking of doing is moving these 2 electrons onto this to form a double bond. No, you cannot do that. Nitrogen currently has 8 valence electrons. It cannot break the octet rule, right? Everything in group 2, carbon, nitrogen, oxygen, and fluorine, will never have more than 8 valence electrons. So we cannot do that. We have to leave this formal charge as it is. So let's just draw this a little bit nicer. But you see, we arbitrarily made a choice. We pulled the double bond from oxygen, from the top oxygen, but not the bottom oxygen. But both of them would have been just as good of choices. And so there's going to be a resonance structure here, right? Where this top oxygen now bears the negative charge, and this bottom oxygen has the double bond, right? So this is the correct Lewis structure for nitric acid. You see, it has resonance structure. And if we think about what the bonding order here is, all of these bonds, all these nitrogen-oxygen bonds, or these 2 on the right anyways, are 1.5 bonds, right? Half the time they're 1, half the time they're 2. So on average, they are 1.5 bonds. One more, let's do OCN. So go ahead, pause the video, and then we'll go through it. OCN minus, my bad. Pause the video, go ahead, we'll go through it. So valence electrons, oxygen has 6, there's 1 of them, so that's 6. Carbon has 4, there's 1 of them, so that's 4. Nitrogen has 5 of them, there's 1 of them, so that's 5. And then we have a negative charge, so that's an additional 1. So we go ahead and sum these up to get 16 valence electrons. We put the least electronegative in the center, which in this case is carbon. So O, C, and then N, and then single bond everything. That's 4 electrons used up, so we have 12 left. We start putting octets on the most electronegative atom. So we put 6 on this oxygen, and then 6 on this nitrogen, and then we're out of valence electrons. So carbon here does not have an octet, and so we want to give it an octet. But now the question is, do we pull those electrons from oxygen or nitrogen? Well, to figure that out, we can calculate the formal charges to have a hint of what to do. So go ahead, pause the video, and calculate the formal charges. All right, so if you calculate the formal charges, this oxygen is -1, this one's +2, and then this nitrogen is -2. So let's think about what kind of hints we can use, right? We know that these positive and negatives can cancel one another out by forming double or triple bonds, right? But we also know that the most electronegative atom gets the negative charge. So if we pulled the electrons from oxygen, it would lose its negative charge, and this nitrogen would have a remaining negative charge. So we don't want to do that. So let's pull the first one from this nitrogen. And so what we're left here is this, and then we have to recalculate our formal charges. So this will be +1, -1. And now we have to do this again, right? Carbon still doesn't have an octet, and it still doesn't have a formal charge of 0. And again, the reasoning here is the same. We don't pull them from the oxygen because it's more electronegative, so we're going to let its negative charge stay there. We're going to pull from the nitrogen. And so when we go ahead and do that, calculate our formal charges. Now we have the oxygen with a -1 and the carbon and nitrogen with a 0, right? And that makes sense because our atom was already negatively charged, so something's got to have a negative charge. So we just indicate this formal charge with this negative here, and that is the correct Lewis structure for OCN. So there's a lot of information here. It is not the easiest thing, but with practice, you can get it. And after a while, you know, it becomes fun. It's like a little puzzle / game. So this is something that you want to be good at.